Hello and welcome to today's webcast. My name is Jimmy Carroll. I'm an editor for Vision Systems Design. The speaker for today's event, Liquid Lenses and Their Benefits for Machine Vision, is Mark Ventura, Vice President of Sales and Marketing at Optotune. Before we begin, I'd like to cover a few housekeeping items. If you have any questions or issues during the webcast, you can click on the Ask a Question area of the console. We'll try to get to as many questions as possible. If you have any audio issues, please try refreshing your page. If this doesn't work, or if you have any other issues during the webcast, again, please click the Ask a Question area of the console, and a member of our webcast support team will work with you to correct the issue. For convenience, this presentation will be available on demand within 24 hours, and a reminder email message will be sent to all registrants, and this can also be found on our homepage. Before we begin, I'd like to thank Optotune for sponsoring today's webcast. And now it gives me great pleasure to introduce Mark.
Hello, everybody. Thank you, Jamie, for the kind introduction. It's great to have so many people signed up and attending for today. We're going to speak about focus tunable liquid lenses, and in particular how we apply those to machine vision. So let's get right into it. The agenda for today is I'd like to introduce Optotune, then the liquid lens working principle, then show you a first overview of applications. Then we deep dive into how to combine electrical lenses with off-the-shelf optics in different configurations. Then we'll review those applications with that prior knowledge, talk about some custom designs, and close with what else you need, like the drivers and the software, and how to get these things integrated. So, about Optotune, we established 11 years ago, 2008. I'm actually one of 3 founders. We do tunable optics, a whole bunch of optical components that move around. I'll show you in a bit. We sail internationally. Right now, 125 people in Switzerland, and we've got 60 people in a factory in Slovakia. And we distinguish industrial business, which is this machine vision area, for example, but also we have a consumer business, which we talk about a little bit less in this webcast. Now, the 4 product lines that Optotune provides are mainly focus tunable lenses. We'll dive into that in a minute. Then we also do other optomechanical components. Top right, you see laser speckle reducers. Essentially, those are moving diffusers that reduce speckle noise that occur at a screen when you project a laser picture, for example. Then bottom left, you see a product that tilts glass to do pixel shifting. We call that an extended pixel resolution actuator. And on the bottom right, you see a 2D mirror. It tip tilts in 2 axes, so online you'd also see videos of that. It's something like not a galvanometer with 2 mirrors, it's in one. It goes in both axes, and it's very interesting for beam steering and potentially for LiDAR for fast scanning in 2 axes. So now we deep dive into the liquid lens and its working principle. So here you see 2 animations. I hope this plays for everybody. On the left we see a mechanical solution, on the right an electrical solution. Actually, the left and the right concept can be actuated mechanically or electrically. The main thing is that we start off with a container. It has an optical fluid inside, and the blue surface is a membrane made of an elastic polymer, and that closes the container. And then by pushing a ring onto that membrane, we can flex the lens positive when we push and negative when we pull. So the lens can go from convex to concave, as shown on the left image. Now, the electrical lenses, they differ a little bit in the sense that the lens shaper ring does not move. It's in its same position all the time. That allows for better tolerancing towards the outer housing, for example. And then the actuator is in this ring outside of the lens and will push up and down. So that's a very natural way to focus, because it works like your eye, basically, except that it's faster. So a few key specs here are that apertures, they go from about 3 to 30 millimeters in size. So we really have different products to match different sensor sizes and different applications. One key thing is that we use one liquid in our lens. This is different than electrowetting, which has two liquids. And the liquid we use has a fairly low refractive index of 1.3, but it has a very high Abbe number, over 100. This means very low dispersion. The benefit is that you can add this lens to an existing optical design without introducing any color aberrations. That's why actually a lot of these things that we combine our lens with an off-the-shelf optics just work, because we have basically an achromat with our lens. Then lifetime, long lifetime, we've tested well over 1 billion cycles without any impact on performance. So it's really okay to focus frequently, multiple times per product, for example, and to go into 24/7 operation. Then on the repeatability, we specify below 0.1 diopters. Maybe after this webcast you'll understand what that means. This is quite good, as the 0.1 diopters is usually within your depth of field. And we achieve this repeatability by employing temperature compensation. I'll get to that a bit later as well. And this means that once your system is calibrated, it can actually run in open loop, basically jumping from preset focus planes back and forth without having to close the loop with autofocusing or using the image, for example. Then on the response times, smallest lens EL310 is the fastest, with response within a millisecond and settles after about 4 milliseconds. And then the larger lens EL1640 would respond with about 5 milliseconds and settle after about 20. But that still is fast enough to focus 50 times per second. So you can imagine how fast your equipment can run with this kind of focusing speed. Now, specifically for machine vision, I like to highlight there that a few benefits. So I'm sure everybody is aware of depth of field. Every lens that you use has a certain f number, and with your certain pixel size, you determine, and your focal length, you determine what is the depth of field where everything is focused. Now, of course, you can increase the depth of field by reducing or increasing the f number, closing your iris. This will work to a certain extent, but then you start at some point losing resolution when you reach a diffraction limit, and definitely you need a lot more light. Now, the liquid lens approach is obviously that you have your liquid lens, which can change its shape and thus focus at different working distances, and that gives you, first of all, a large working distance range. And then a very fast response, so you can do fast recognition. You can actually use now less lighting, because you can operate maybe at a lower f number than you could have done with a high f number to extend your depth of field. And one benefit which we find is actually quite important is the ease of installation, or the flexibility that you have in your production line. Because nowadays there's a lot more variance in what is to be produced. Bottles change their size, you have different products on the same line, and being able to focus remotely, for example, through your internet back end of your machine, allows you to make adjustments without having to dispatch somebody to the customer site, drive there, open up the machine, fiddle around with the optics by hand, put everything back together and drive back home. So definitely a lot of flexibility. So now let's move on to a few applications. I'll revisit them later, so I'll keep it brief just to get you a bit motivated here. Barcode reading is a clear application where you have packages at different distances, may that be handheld or fixed-based. Then package sorting is a classic where you have different sized boxes that have obviously a different distance from a camera which is mounted above those boxes. Then the lens can be on a robot which can inspect something like an engine, for example, and depending on the field of view you want, you position that robot, and if you're closer you'll have to refocus, but you'll get higher magnification. And bottle inspection, for example, different sized bottles, you can look through the cap and see the bottom of a bottle. Then some more shorter working distance examples include electronics of all sorts. Then contact lens, I really like that because they're not flat, obviously. As our lens in the eyes are not flat, that's kind of related to what we're doing. So you can step through those different positions or like depths of the contact lens. Same holds true for jewel inspection, where you can find inclusions or defects at different depths inside the material. And on the top right, we show a laser marking system where it is beneficial to monitor the laser spots and how it welds or cuts or whatever it does. And you can do that inline, and there are some systems you can go inline with your laser beam and vary the focus with our lens as well. Then telecentric lens applications. For example, on the left, camera phone lens inspection. So you have several layers of plastic components in a camera lens stack, and with our lens you can basically tune a bit through that stack and see dust and scratches at different levels. And now a very nice one is IC inspection by using a telecentric lens, and on all sides of the IC you can place a 45-degree mirror. So you can, with one shot, you can look at the top, but also the sides. Maybe not with one shot, with one camera, because there's a different path length between the top surface and the side surfaces. So that's where you use the liquid lens then to refocus between the two. And for high magnifications, inspection of large surfaces such as liquid crystal displays or PCBs, where you move over a fairly large area, and if you have a high magnification, your depth of field will be really shallow. So the mechanical tolerances hardly make it possible to stay focused as you move around with a inspection head. Then I like the liquid inspection as well, particle counting, or looking at blood to see certain things. So you can scan through a liquid, and basically with a shallow depth of field you can then even count objects in 3 dimension. And microscopy, where you have a very small depth of field because of the high magnification, is particularly interesting as well. There's quite a few different types of microscopes that have already been using our lenses. Then I'd like to share, just for to be complete here, a few applications from the non-imaging space. We do quite a bit with ophthalmic equipment, so where our lens is used for human eye refraction, or basically refraction correction, such as visual field analyzers or phoropters, the equipment you use at the optometrist when you get your prescription glasses. Then there are laser applications. The laser marking, actually, before we looked at inspection for laser marking, but also you can place the liquid lens in the path of the high power laser up to about 50 watts in the near infrared, and you can mark on curved or slanted surfaces. Then laser projection means that you use a projection tool to show an operator, for example, where to punch a hole, and as the distances vary, you can adjust the focus there too. And OCT, the bottom example, is either looking at the retina or something else where you can look into the material. The lens can be used there for focusing. And there's a bunch of illumination applications. For example, medical headlights, you can benefit from a liquid lens to collect the LED light, and as you change the focus of the lens, you will have either a larger spot or a more focused spot size of that LED. Alright, so now comes the more technical part here. Let's look at how to combine our lenses with off-the-shelf optics. Now we separate 4 cases. Endocentric lenses, our lens can go either in the front or at the back. Then telecentric lenses and microscopy. So when we go in the front of a lens, we typically mount in the filter thread, and we go for applications with a fairly large working distance, from 100 millimeters to infinity, or in that range. Then when you place our lens at the back, if it's a C-mount camera here in this example, actually our lens acts like a distance ring, and your object plane will come closer. So this only works with long focal lengths, and it's typically then used for short working distances where you get very nice results for macro type imaging. Then for telecentric lenses, it's essential that our lens is integrated fairly close to the aperture stop. There are several models available that have done that. We have magnifications in the range of 0.13 to 4x. And in microscopy, you can go to up to 100x magnification, so it depends all on your objective lens that you use underneath. And I'll go into details later. There's two options, one with or one without magnification change while you're focusing. So let's look at endocentric lenses, the front lens configuration. That's actually the most straightforward. Definitely on the right, you see a C-mount camera, C-mount lens, and most of those lenses have a filter thread. And we have included the typical filter threads from M25.5 to M30.5 to be part of our EL1640. And with that, we can just mount onto the C-mount lens. Now, there's also S-mount lenses that can offer a very cost-effective solution for smaller sensors, and actually it's quite nice. These S-mount lenses with a S to C-mount adapter, they can mount inside the thread of a C-mount camera, and there's enough thread left to mount a C-mount lens right on top of that. So the left example shows something very compact, lightweight, and cost-effective that can deliver very nice results as well. Now let's go a bit into a few calculations on like how do I find out my working distance, how does it relate to the focal length of our lens, and so on. So on the left you see a chart which shows optical power in diopters versus current. So first of all, optical power in diopters, this is the 1 over the focal length. So this has many advantages we're going to see in a bit, but what's great for our technology is there's actually a linear relationship between current and the optical power of a lens. And now we can engineer this relationship depending on, for example, the liquid fill level. We can add a vertical offset to this curve, or by changing the stiffness of a membrane, we can change the inclination. So you can imagine if a membrane is, let's say, twice as thin, then with the same force of the actuator, it's going to move twice as much. The membrane basically acts like a spring. And this way we can engineer, design different curves that suit different applications. And now back to this diopter value, the benefit of that is it can be added arithmetically. So focal lengths we would always add 1 over f together, which is not that simple, and the diopters you can just add together. And now if we look at working distance, we can figure out in front lens configuration easily what the working distance is by the formula shown in the middle here. And I think the examples make it most obvious. If our default working distance would be infinity, so let's say C-mount lens is focused at infinity, you haven't used our lens yet, then you put our lens in front. If the optical power is 0 diopters, which would mean infinite focal length or a flat piece of glass, then the working distance does not change, it stays at infinity. Now if we load 5 diopters onto our lens, then the working distance will result in 1/5 of a meter. And now our lenses typically go from, for example, -2 to +3. So the best way to use them frequently is to set the default working distance to 0.5 meter. And then if you apply -2, you basically focus again back at infinity. And if you apply +3 diopters, you focus at 1/5 of a meter again. So again, you have your delta of 5 diopters. You're just using it from -2 to +3. And here's a matrix showing more examples. Some of our lenses have up to ±10 diopters of range. So basically, you can imagine a system that focuses from infinity to 50 millimeters. But the most common configuration is really what we just discussed, from about infinity to 1/5 of a meter. Now, I'd like to also discuss a limitation of this front lens configuration, because if you place our lens in front of a C-mount lens, you do also have some mechanics that start to obscure the light at some point. So in this example, we're looking at a lens of 12 millimeter focal length, and let's say we have a 1/2 inch sensor. Then we see that the horizontal field of view, the angle that we get, is 28 degrees, that's all fine. It will pass our lens. That works well. But now let's go to a 2/3 inch sensor, and with the same focal length, we get a bigger angular field of view of 38 degrees. Now, as you can see, partially we will be hitting our housing there, so definitely some marginal rays, I mean, at least half of the marginal rays will be lost, so definitely at 38 degrees you'd have some severe vignetting. So there's a limitation into what a certain angle that you can achieve, and our rule of thumb is roughly 30 degrees is okay. And now here this table shows basically this consideration graphically. On the left we see different sensor sizes going from a 1/4 inch to 1 inch, and then a 30 millimeter image sensor length, or that could be the diagonal or the length of a line sensor. And then to the right you see the different focal lengths from 6 to about 100 millimeters. And what we see here is this diagonal line where we see that at 30 degrees we're basically okay or have some slight vignetting. But if we now want to go for example, a larger sensor like a 1 inch, but also have a short focal length like 12 millimeters, then the angle would be 56 degrees. Now, we don't have anything that works like that off the shelf, but it's possible to achieve that with a customized optical design. Talk about that a bit later. So we have some developments ongoing where we try to push these boundaries here and provide more solutions than you can just find today off the shelf. Now here I have one more example of a front lens configuration with a fairly large field of view. It's a 7.2 millimeter S-mount lens. So I just include this to show that actually a 53 degrees horizontal field of view is actually possible. And you can see here the lens will be mounted in the camera, in the C-mount camera again. We use 15 millimeters of extra spacer on top, and then comes the liquid lens. So this could be the configuration to recommend for the most or the largest field of view possible on a C-mount camera at the moment. So now we switch to the back lens configuration. So here we see all off-the-shelf parts, standard 50 millimeter lens, and our lens will go between the camera and the C-mount lens. Now this can be either our EL1030 series or the EL1640 series. Both are available with C-mount on either side. Now this introduction of a distance ring at the back basically means the object distance cannot, the working distance cannot be infinity anymore. It has to be less. And because we introduced 20 millimeters of distance, this whole concept only works with focal lengths which are at least 35 millimeters in focal length. And in this example we use a 50 millimeter lens, and some results here show that our typical working distance would be in the range of 160 or 200 millimeters. And the Z range that we get would be maybe 25 or 40 millimeters. So this is a much smaller working distance change than if we'd say we go from infinity to 1/5 of a meter that we discussed before. But it's a different concept here. So we're in a macro situation, and if you're looking at something like electronics or something smaller, then actually 40 millimeters of Z range is quite significant. So this is indeed a very useful configuration. Now, actually, we'd like to have this imaging lens move even closer to the liquid lens, and there's one configuration I'd like to share where this is possible. It happens that the Schneider Xenon Topaz lenses, they have a special adapter piece that goes from some other thread to C-mount, and it's actually possible to use a shorter adapter. So by using that, we can get, in the same kind of back lens configuration, we can achieve longer working distances, for example here, or larger tuning ranges, I must say, as well. Here we show 128 millimeters to 204 millimeters, so that's quite a big Z range of 70 millimeters. And yeah, it's a very good quality lens, and on a 1 inch sensor that performs very nicely. And the 16 millimeter clear aperture of our lens is enough not to introduce any vignetting. Yeah, now here's an example with M42 mount cameras. The benefit of these cameras are that the flange to sensor distance is a bit shorter, and also M42 mount optics, they usually have a flange to sensor distance of at least 45 millimeters. Now this offers enough space to have the liquid lens mount at the back, and in this case we do that with our EL1640, which has one configuration labeled with M42, so M42 on either side. There will have to be, depending on the lens you use, some additional spacers. In this case we use 13 millimeters to get to the camera. There's another 12 millimeters inside the camera until you hit the sensor. And with this configuration we find that the sensor, which in this camera has a 30 millimeter diagonal, is fully illuminated. You see a comparison of a white object without our lens on the left, with our lens on the right. So even at the low f number of 4, we see that there's no introduction of any vignetting. So this is a really nice configuration, offers also very decent tuning ranges. In this case we tested 1.1 meters to 0.38 meters, which would be a typical use case for logistics. Then the next example is something very similar with a 75 millimeter lens. It's just a special designed lens. It's intended to have a 1x magnification, so the object and the sensor is at the same distance from the lens. I won't go into too much detail here, but we get also nice results, very low distortion, and actually fairly large Z range of 57 millimeters achieved here. And again, in this case, we don't reduce the resolution of the system. It's in line with what the Rotagon lens here can deliver. Then last back lens, or yeah, this is not really a back lens configuration, but I'd like to just share it briefly. These long, for inline inspection laser marking, you need a very long focal length, because what you're looking at is pretty far away. You want to have high details, so these are typically 150 or 300 millimeters in focal length. And actually Sil Optics has lens models which can be taken apart. They have an M42 thread where we can fit in behind the first lens group, and I believe there's a second lens group in the back. But that's a nice configuration if you would want to do something inline and laser marking, or just really something really far away with a high magnification. Now, it can be a bit confusing to find the right lens and the right sensor, and make sure everything is you got your right field of view. So we offer two tools for that. One is a configurator on our website. Here's the link in the title. Here you can enter an object size, so the idea is your object size in X and Y, and a working distance range that you'd like to cover. So this could be, for example, the size of your package, and then what is the tallest package and the shortest package, gives you two different working distances. And then you can choose an optical configuration, including a sensor size, the liquid lens, then there's different endocentric lenses here, and you can also choose between front and back lens configuration. And then the goal of this configurator is to generate the blue line that goes through the green box. That's simply put. So you can make sure that you cover enough field of view and that you cover enough working distance to solve your application. Now this tool will, the focal lengths used here, I know it says Tamron, but actually it doesn't really matter what brand you use. We just started out with a few, but it's just mainly you choose the focal length. But there are a few differences in brands, and we have come across a few brands which we can recommend more than others. So in this other tool here, which we call the lens selector, you start out similarly. You enter your field of view and your working distance. Then the angular field of view is calculated. You see the same matrix we've just seen before, and you click then on one of those cells, and it will bring you to a page, for example here, for 1-inch format sensors and 35 millimeters focal length. And here we now list specifically which imaging lenses we can recommend. Some will be listed multiple times. We see that we have your front lens configuration, back lens configuration, and every now and then there's actually a test report that we can either share online or upon request. We comment on the vignetting, we comment on the smallest pixel size that you should attempt with this configuration, and any additional comments. So we will be updating this database of solutions as we come across them, and if anybody would like to contribute, for example, like if they found a lens that works particularly well, may that be from a mechanical reason or from an optical performance standpoint, we'd be happy to add that. Then let's move to telecentric lenses. So with telecentric lenses, it's a bit more difficult off the shelf. Now, mainly, if you just put our lens between the camera and the telecentric lens, you will get some tuning of the working distance, but actually not a lot. So what is really better is if you can integrate the lens close to the aperture stop, and we've shown that initially with some lenses from Moritex, which can be disassembled, and then Optics came around with a few designs that were specifically designed for our lens, and with this we have seen that we call this the optical leverage. So how many millimeters of working distance can I change per diopter that I apply to the liquid lens? And we see here great performance, meaning large Z ranges and very low magnification changes. So this is the way to go, and I'll present now a few of those telecentric lens designs. This is the one we just talked about, Optics 2x lens. It's actually also rated for large image circles. There's a test report available on that online. I won't go into details here. They have then doubled down with, I think, 16 models of different magnifications. Some of them have coaxial lighting included. Then there are some other brands too, like VST has released 4 models from 1 to 4x in magnification. Note that these are for up to 1-inch sensors in this case. Actually, the THV models have a very high resolution, so definitely, for example, suitable for the Sony 1.1-inch sensor with 3.5 micron pixel size. Again, here there are some test reports available. Then Edmund Optics has integrated our EL1030 series into their Mercury lenses. Those are 4 models ranging from 0.15 to 0.75. They are for slightly smaller sensors, but they do have a good resolution. There's a demo video on that as well. And then most recently, a Chinese company, Linku, has integrated the EL16 into 4 models, and actually they are very close to really being bi-telecentric. And here we have magnifications from 0.36 to 2x, whereas the 1 and 2x, or at least the 2x, is not such a high resolution design, I can already say from here. But there's again here some test reports. Also very nice integration. So yeah, this gives you a bit of an overview of telecentric lenses. And now to the last chapter on here, microscopy. There are 2 main ways to integrate our lens with microscopes. You can either squeeze, I have to say squeeze our lens behind the objective lens. This can be done with C-mount or some thread adapters. And that actually allows for pretty large working distance changes. So, for example, on a 40x magnification, we can shift the focus by 160 micrometers. Or if we use a lens with 20 diopters instead of just 5, then we get 4 times that, which would be 640 micrometers, which is plenty for that magnification. Now, however, when you do that, there is a significant magnification change, because by focusing, we're also bending the chief rays, and that changes the magnification. Now, to avoid that, there is a design approach where our lens is placed at the conjugate pupil position in a relay system. So basically, you have your objective lens, a tube lens, and then usually you'd have your camera at an intermediate image plane, but from there you attach another relay optics with a 4F system, and our lens would be at the pupil position in between. And by doing that, when you focus, you do not bend the chief rays, and actually you can keep the magnification constant. However, the tuning range is considerably smaller, but still, you have several 10 micrometers of range, and here especially the 20 diopter lens can give you a bit of a boost to get some more Z range. So this is something that of course, has to be designed. There are optical designs out there that do that, but I don't have time to go into more detail. Now, instead, I'd like to share a few industrial zoom systems. For example, Optem Fusion is by Excelitas, a system that has a mechanical zoom, and the liquid lens is designed into a module that can be placed below the zoom. And that's actually a good position to place the lens, because after you've focused, you can then zoom and you stay focused. This behavior is called parfocal. Then there's also industrial zoom by Edmund Optics, where our lens is placed behind the zoom. So this design now is not parfocal. That means when you change the zoom state, you will typically have to refocus the object. There's also a little nice configuration which I call a low-cost microscope. You can actually take a standard imaging lens and use it backwards. So you place the object where usually the sensor would be and image it backwards and go through the liquid lens and after an empty tube back onto the sensor. So this allows for a fairly compact and low-cost system for magnifications of maybe 3x, 4x. We could also go to 5x or 6 with a different focal length. So this is something you could put together yourself, but actually Edmund Optics has done exactly that as well, with two designs that offer 2 and 5x magnification, and pretty nice performance at a reasonable cost, and especially very compact. Now, the applications I mentioned before, I have added here now the actual optical configuration that has been used by some customers in that application field. So the structure is always the same. We show the application here, and on the left you see which sensors were used, which lenses were used, etc. So the one I'd like to start with is package sorting. Here actually you can go for a line sensor. It's possible to use a 40mm line scan camera. I think the typical resolution here would be, well, a 5-micron pixel pitch would be maybe suitable for this kind of lens. It's the back lens configuration with the 60mm M42 mount lens, and this is the typical use case for package sorting with a working distance range of maybe, for example, 800 to 1,500 millimeters. Then the bottle inspection case would be, for example, a 2/3 inch sensor and a 35mm C-mount lens, and then REL 1640 attached on the filter thread. That gives you a fairly small angular field of view of 14 degrees. And it's easy to achieve a working distance range of, from example, 150 to 550 millimeters. On the bottom here you see the screenshot from our configurator. Now obviously if you are at 150 millimeter working distance, you will have a bit of a smaller field of view, because we're not zooming, we're just changing the focus, so your angular field of view stays pretty much the same. So your horizontal field of view would then be maybe 40 millimeters, and at your biggest distance you could have bottles with a bottom size of over 120 millimeters. So that's pretty much in line with the type of bottles you'll find out there. Then the robot vision I mentioned, S-mount configuration, which is fairly compact and lightweight. So I think this is a very nice solution. 1/2 inch sensor, 12mm lens, gives you a 30-degree field of view. And for example, the feature here, which I really like, if you need to have an overview picture, then you just move the robot a bit further away. You can maybe see the entire product. And then if you need to inspect some detail, you just go close up. And if you go from like 1 meter to 0.2 meters, which is again 1/5 of a meter, right? Then you will actually, this will result in like a 5 times zoom. So you just go close, you refocus, and you have a 5 times higher magnification. So that adds a lot of versatility to your inspection system. Then the contact lens case was a back lens configuration, 2/3 inch sensor, EL16 at the back, 50mm lens, and the resulting like three-dimensional field of view, I would call it, has a size of 28 by 21 in X and Y, and 45 in Z. So definitely high enough to inspect contact lenses, even including the packaging, which is usually also curved. Then electronics inspection. This is a system that I'm showing actually from a partner company that has done very nice software that includes a continuous autofocus algorithm. So basically an operator can put a PCB on this table, move it around, and as the object heights will change, the software will automatically refocus. You can also acquire image stacks, and with that 3D information, it's called depth from focus. So that's actually a very nice, powerful software. And again, this back lens configuration with the 50mm lens here with a bit of a bigger sensor size results in 40 by 30, again by 45mm, which is a quite nice field of view for high resolution on electronics. Then the dual inspection case is again a back lens configuration. Now actually in this case what we've done is we added an additional 20mm of distance rings between our lens and the camera. So this means the working distance is even closer. I think in this case it ends up between like 90 or 100mm, and that also gives a bit higher magnification, which is beneficial in this case, as those jewels are not quite that big, but you like to have a higher resolution. So what is maybe not quite clear to you from this picture, this is just an additional, this is Photoshop basically. It's an additional spacer which was put in between, but we didn't have the picture available. Then the telecentric lens, in this case I show you the VST 1X lens for the 1.1 inch 12 megapixel sensor. It presents really nice resolution, very linear, also linear scaling from the minimum to the maximum working distance, and there's a very detailed test report available on that if you're interested. And with this kind of camera module, the key thing is you can step through different layers, and that can basically can look into the camera module through the optics. It's quite interesting. Then this telecentric case with the mirrors, what you need there is a fairly low magnification. So here we use this 0.15x telecentric lens, which has a pretty big entrance aperture, and the field of view you get there is like 40 by 30mm, and actually the Z range is it's way too big. It's over 50mm. Then there's actually another industrial zoom case from Optem, a Chinese company. They have a typical, like a mechanical zoom system, and again our EL can be at the bottom, designed in, and actually they did a nice job with the software as well. So there's a automatic control of zoom and focus, which can be pre-programmed. So that's I think also a very neat way to integrate our lens. And the last example is the liquid inspection, or in this case blood cells. Actually at a 6x magnification you can start to count blood cells, and this is the low-cost solution with this inverted imaging lens. It was a 16mm lens inverted, and our lens in an empty tube above it. Field of view there is in the range of 1.4 times 1 in X and Y, and about 0.8 in Z. So definitely a small field of view, but if you have such a high magnification, you know how difficult it is to find the right focus, and this can be a big time saver to have the electrical focusing capability. Alright, so custom designs is something I just can touch briefly because there's not too many published yet. One that I can show you is from Kova. They designed a 35mm lens for 1-inch sensors, and what they did is basically they cut off their imaging lens behind the aperture stop, and our lens follows right after that. But taking into account our lens, the whole design was optimized, and they achieve a very nice resolution, great MTF, the simulations here on the left, and it's rated for the 1-inch sensor, so definitely you'll get a better performance out of this customized solution than taking an off-the-shelf lens and just putting our lens in front, for example. This will perform a bit better. And also for the 50mm large format lens, we have a model from Chance for Change 50mm design, which is rated for actually even bigger than 1.1 inch. It's a pretty nice image circle, and our lens is designed in at the aperture stop, and it really leads to a very nice imaging performance. High resolution in the order of 140 line pairs, and with an f number of 2.8 there's like a little bit of vignetting, but not much, and with f4 we can go without vignetting. So this could be a really nice one for high resolution, high quality imaging with a fairly narrow field of view. So yeah, if any people from the imaging lens industry are listening, it's definitely the best thing to do is integrate our liquid lens close to the aperture stop, optimize the optical design, and then we can get out a little bit more performance. So we are working with some partner companies to increase the offering on those integrated designs. Especially challenging are the big sensors and short focal lengths that result in big fields of view. So there's going to be some designs coming out soon addressing those areas where we cannot work with off-the-shelf optics. Okay, we're soon there. Let's look at the drivers and the software. So once you've figured out the optics, you want to, of course, know how do you now attach the lens and drive it from your system. Now, at the moment, we have 3 drivers available off the shelf. Optotune provides a USB-based driver, and from Gardasoft, we have an Ethernet-based driver and an embedded driver. Now, in terms of performance with our lens, they're all very similar. The CL180, the industrial driver from Gardasoft, has a bit bigger current range, so this would help maybe push the Z range in cases where it's a bit tight. For example, in microscopy, you can get a bit more range out of it. But usually, the tuning range is actually rarely the issue. There's plenty of focus range with liquid lenses. So the main differences are the interfaces. Our interface on the Optotune driver is a USB 2. There is some analog in, but I must say I don't really recommend it, as the Gardasoft analog in performs better. We provide some source code in C#, but we don't have like very detailed SDKs available, I must say. Then the Gardasoft driver is mainly used through Ethernet or RS-232, and what's nice with this one, it includes oscillation modes. For example, sinusoidal oscillation or a sawtooth or a triangle form, and you can load it with custom waveforms that can be started upon a trigger-in signal on the analog input. And another nice feature is the lookup table. So if you have a distance sensor, we'll talk about, I'm jumping ahead, but if you have a distance sensor, you can program the driver to address different optical powers depending on the analog voltage, and this configuration can be done over the Ethernet port through the built-in browser, for example. And then once this is done, you can actually unplug the Ethernet again, and it will run standalone off of the analog input. That's a really nice use case. And then for this embedded driver, the interfaces are I2C or UART. So there's 2 pins for that, which can be configured by software. And the idea of this is to interface to a microcontroller or an FPGA or a camera that provides the serial interface. It also contains the analog in, so that's pretty similar in terms of functionality and firmware. It's very similar to the larger driver, but it's of course more compact, lower cost and higher volumes. And here is really the goal to get this integrated into cameras, maybe into our lens in the next design, and make it all a bit more integrated for OEMs. Another feature I'd like to talk about is what we call focal power mode. So our lenses are basically current controlled, but there is an influence of temperature. The higher the temperature, the more the liquid expands, and that leads to a slight positive drift in optical power. Now, good thing is there's a temperature sensor integrated in our lenses, and each of those lenses is calibrated during OQC. So we measure optical quality on a wavefront sensor, but also the characteristic of optical power versus current. And that data is saved on the EEPROM of the lens. And together with the current temperature, the driver can then calculate what is the best current to output to the lens to achieve a certain optical power. Accuracy achieved here is in the order of 0.1 diopters, actually even quite a bit better depending on the use case of the lens. Now, how to find the right focus? This is depending on the application. Image-based autofocus uses camera images as feedback, so maybe there's different strategies, but let's say you step through the whole Z range, maybe 10 to 15 frames, and you just pick the one which has best focus, or you maybe want to converge on with some algorithm on the best contrast image. The issue there, of course, is you're never completely sure whether you found the best focus. So if you do defect detection on glass, for example, so if you don't find any particles, it just might also mean that you just haven't found your focused frame. So you just have to be a bit careful how this is applied in the application. Typically it's used for calibration purposes, or if there's an operator involved who can basically verify the image. Then preset lookup tables is quite straightforward if you know what you are inspecting. So let's assume you have products A, B, and C. They have different heights, so each of those products would have just a different optical power stored in some lookup table. This can be then run from a PLC or some other system who knows which product is being inspected. Then if you do not know what is being in or what is coming along, you could use a distance sensor, and then the distance reading can be mapped to a certain optical power. Maybe you have to calibrate several points for that, and then the system can just accept whatever comes, like for example packages in a conveyor belt, and then the sensor, if the sensor reading is right, your image will be focused within one short step. And this is actually a setup we like to show at our booth at trade shows. So there's a system we show with a rotating turntable of packages of different height, and we use a sensor that outputs 0 to 10 volts analog that's fed in directly into the Gardasoft controller, and who performs the lookup standalone, so we're not using the image in this case. And what's nice is we can measure the latency of this whole system. So actually the distance reading to conversion to current, including the settling time of our lens, is in the order of 20 milliseconds. So this means that if you run a conveyor belt at 5 meters per second, you could take an image every 100 millimeters. And that's pretty swift, I would say. The next slide shows details on our USB-based driver, which is under Windows pops up as a COM port, and under Linux as a file. So any software that can read or write to a serial port can communicate with our driver. There's a few typical commands like set current, set focal power, and so on. This is described in a detailed spreadsheet, so we're happy to share that, and also some sample code in different languages. The next slide, we see some software partners. So if several of these companies have implemented our driver, may that be like a DLL or just like a script that can be added. So if you see your preferred software in that list, reach out to them. They might already have done the work for you. Okay, and then as a last slide, and thank you for spending all this time with me so far, I'd just like to summarize again the different lenses that we actually use in the machine vision field. EL1030 and EL1640 are typically the lenses that are used for machine vision. They have different form factors, different threads, C-mount for example, but also metrical threads for filters. And they also have OEM versions which can be designed into optical systems as you would design in a glass lens, for example. There's different optical power ranges, and we discussed the smaller the lens, the faster it is. And with that, I would like to close, and thank you again for your interest in liquid lenses, for spending time with us today, and if there's any questions, I'd be happy to take them now. Thank you.
So the first question I have here asks, can you comment on the hysteresis of the optical power versus current graph? Is there any hysteresis when changing lens curvature one direction and then reversing the curvature?
Yeah, so we measured hysteresis as well as part of our OQC. Since we use a voice coil actuator, which is attached to the membrane, there's inherently like no mechanical friction. So I'd like to say there's no hysteresis at all. But of course, nothing's perfect, so we do measure, but the hysteresis is in the order of like 0.01 diopters, which is like really, really within your depth of field. And typically you will not see any difference if you approach a certain position from the bottom or from the top. So we can really confirm that hysteresis is not something customers typically have an issue with. And if there's any effect that could be concerning, it would be more temperature related. So if there is maybe a big shift in temperature, or if you do like very big steps, then maybe there could be some drift that, before the lens completely settles. But that would again then be reproducible if it's based on temperature. But for, I would say, 99% of the cases, we don't see any hysteresis issue because we have no friction in our system, no mechanical movement, or no touching at least.
Thanks, Mark. This question asks, is the system usable from a Linux machine?
Totally. I mean, our lenses can be used with any camera and any kind of software principally, okay? Now, our driver, this is maybe what I started to explain when I dropped out. I'm sorry about that. So our driver pops up as a COM port in Windows or as a file in Linux where you can read and write over a virtual COM port. And it works perfectly in Linux as well. And I'm assuming everything that Gardasoft provides will have Ethernet interfaces that also work under Linux.
Thanks, Mark. This question says, what about vibrations? Could this be a problem at high accelerations?
So definitely survival of the lens is not an issue. We've done plenty of shock tests. You might think they're fragile because there's a membrane inside. It sounds a bit fragile, but actually, it's a very elastic membrane, and they don't break because of any shock or vibration. We actually don't have any complaints either because of vibration in operation, but I don't really have that much data to provide, although I have seen a few machines which were rattling at a pretty intense pace where there was no issue, like this bottle sorting machine, for example, which is pretty loud and vibrates. I guess there is a resonance in our lens at maybe 400 or 600 hertz, depends on the size. So it may be a certain resonance. If a certain vibration would trigger that resonance, I could see that maybe there could be some impact. Would have to be seen in the application. But really, so far, I cannot say that this is an issue. And if you do like a high acceleration, for example, on a robot where you jump and you stand still, then you would just have the normal settling time of our lens in the order of 10-20 milliseconds until any kind of ringing due to the stop would have stopped.
Thank you, Mark. Can you drive the lenses with MATLAB?
Yes, MATLAB, I mean, you can drive the lens, as I said, with any program that can access the serial port. And MATLAB can do that. Now, I'm not sure if I think somebody put some MATLAB code online, so there is something we could maybe share. It's not from Optotune, though, but I know that customers have been using MATLAB, yes.
Thank you, Mark. What is the price of these lenses, and where can we buy them?
Yeah, good. That's a very good question. So I'd say the typical lens we look at in all these examples here, EL16, it's in the order of $700–800 list price. Now, some of the higher specified lenses for microscopy with bigger tuning range and better optical quality, like a better waveform quality, it can maybe be up to $1,500. And then some lower specification, or maybe the smaller lenses like the 1030 can be in the order of $300. So that's the kind of price range we move in. And of course, in volumes, prices go down considerably. And we do also have a low-cost product, which is the EL310, the smallest lens. That one has a list price of $120, and in volumes, of course, again, less. And you could find all these prices as well, for example, on Edmund Optics, who distributes us worldwide. So all our standard products you'll find there. And then we do sell through local distributors in most countries. In the US, there's several. In Asia, there's several. And you'll find, well, you can ask your preferred distributor for a quote, but it will be in line with what you find on the catalog. And if there's anything special about your application, if you need a customization, like maybe a different coating for the cover glass, you know, different wavelength or a different adapter or something, we're happy to talk to you directly to optimize or configure it according to your needs.
Okay, thank you. I've got one more question that I'll take here, and then we'll wrap it up. This one says, will you have products that will facilitate lower focal lengths, 8 millimeters, for example, with a 1-inch sensor format in the future that do not have vignetting?
Well, absolutely. Well, 8 millimeters on 1-inch is actually a pretty tough design because you get into very large angles. But as I mentioned, if you design our lens into the optics, you get a lot more design freedom. And then the 16 millimeter clear aperture of our standard product is actually good enough to cover large angles at a decent F number. So we're working on some designs. I can mention that 12 millimeters for a 1.1-inch sensor is in development. And whether this can then be pushed to even shorter focal lengths, we'd have to look. I would say it's potentially possible. But yes, we are working on bigger fields of view, and especially we have many requests for the larger sensors, like the 1.1-inch 12 megapixel. And our lenses are definitely suitable for that sensor. And if we can integrate them into an optimized design, then you also get really good performance out of them. So yes, we're working on that.
Well, thank you very much, Mark. We've gone past the top of the hour, so on behalf of Vision Systems Design, I'd like to thank you and everyone else for joining us today. This presentation will be archived within 24 hours and can be accessed from our website, and a reminder email message will go out. If anybody has any questions about today's presentation, please feel free to reach out to me at jamesc@penwell.com or reach out to Mark. And we thank you all for joining us and look forward to providing you with webcasts in the future.
Thank you very much.